let's start going. So chapter 13. I gave you a handout. Everybody get that handout? I mean, you got a few more here, I'm sure. Who needs the handout? Did you get the handout yesterday? Anybody need it? Anybody? Couple? Anybody else? Everybody got it? All right, that's just to speed things up so you don't have to write out all the words every time, and we can just kind of learn the concepts. So, okay. So, this is the chapter. Remember, it's all about collecting information. What's a wise way to collect information? This is my favorite chapter in the course, so I think it's the most useful. We'll talk about how information is collected wisely or less than wisely. Survey about extramarital affairs was conducted by a columnist. She asked her readers, this is the one we left off on last time, she asked her readers to let her know if they had been faithful, unfaithful, da-da-da-da-da. Based on the data in the table, what's the percentage of married men who were faithful? So how do we figure that out? So you just take the men number here that were faithful over the men total, right? Percentage is always over total, right? So that would be 45,775 over the total, 60,553. I guess that comes out 75.6%. Good? Just faithful, men that were faithful over the total. But based on the data, percentage of men who were faithful to their spouses, married people. So the second one says married people, not just men, but married people. Where are we at? Married people who were faithful. So how do you do that? Married people. Well, you take the what do you do? The total number of people, which you'd have to add up the men and women, huh? So whatever 140. They don't. I wish they gave me the totals. They don't. Well, they give me the total of women. So 149,787, and the total of men 65,500. You got to add those up in the denominator for the total of all people, and then the total faithful men and women. Women 127,317 plus men 45,777. Is that an 8 or a 5? What is that? That's an 8. I couldn't read that the first time. That's an 8. All right. Anyway, yeah, just work that out. That must come out to be the 82.3%. Good on that? So percentages are always over the total, aren't they? So for men, it's the men amount over the total men. For the all people, it's all people over the all people. And then how accurate do you think the estimates in A and B are? And I answered not very accurate. Choose the, and then I gave the reason. The sample was not representative of the target population. Those are the kind of multiple choice questions that you're going to be asked that fool people. This exam actually is one of the hardest for people. It's all the reading and all the little bitty words, I think, that fool people. So let's talk about that a little bit. Why would this study not be very believable? If you read this in some magazine, in this magazine, and it said, here's the percentages of people that were faithful to their marriages, da-da-da-da-da. Why? So 75.6% of men are faithful, 82.3% of men and women overall are faithful, da-da-da-da-da. Why would you not believe that's probably very close to the truth? What could cause this study to be a little unbelievable? Think about, what I answered down here might be a reason that you wouldn't think of. I mean, you might think, well, people aren't going to answer honestly if they've been unfaithful. They might not tell the truth. And of course, that's an important point. Another important point is that the sample was not representative of the target population. What we mean by that, that's really important when it comes to polling and information gathering. If I was just to go ask people in Fresno who they're going to vote for governor the next time governor of the state is up, and I was just to ask Fresno people, and ask 100 people, get the results, and say, here it is. I think this is how the election's going to go for the whole state for the governor. Well, that wouldn't be good because Fresno is different than the whole state in different ways, and and different ways were different. So if you really want to get correct information for the whole state, you have to really take information throughout the state. Take it from different, or at least areas that represent the different kinds of places. For example, we're a farming kind of area, right? We have a lot of agriculture. We probably value agricultural issues and candidates that do that, And so I'd also have to take cities like San Francisco. They're going to probably have different feel on issues than Fresno people, et cetera, et cetera. If you want to do a good survey, you have to make sure you represent the target. You understand what they mean by the word target population? That's what you're aiming at. If you're doing archery, you're aiming at the target, right? If your target is to know the whole state's opinion for governor, then you can't just ask people from Fresno. You got to ask people throughout the state. If your target is to know, what is she doing in this issue? The article here. Isn't her target to let us know what percentage of all people, men and women and whatever, are faithful to their marriages? But she's only asking her readers. That's going to be a different kind of person than the average person in the world, right? Do you see how that skews it? If you only ask your readers, there's a certain kind of person that reads that magazine, certain characteristic. I don't know what, but they're not going to be, and if you took any magazine and you took the readers of that magazine, you would get a different kind of person than the average person in the whole United States, for example. They're going to be a special kind of person, whatever that characteristic may be. So it's not going to be representative of the target population of the whole whatever. Is that making any sense? Am I doing the Charlie Brown teacher 111? Is that coming across? It's got to represent the target. It's got to fit the target. All right. Apple Pencil is working again. I don't know if you were worried about that for me. Remember it just stopped working yesterday all of a sudden, out of the blue? Technology's so crazy. I swore I thought it was broken because it was completely not connecting in. I thought, I'm going to buy a new one. It's $100. That's crazy, So, it's kind of bugging me throughout the day, but I had other things to do, and right at night, about an hour before bedtime, I thought, all right, I'm going to go on the computer real quick and just type in, what you do with everything now, Google, right? Apple Pencil not connecting, da-da-da-da-da. Sure enough, there's like 10 people. Apple Pencil stopped connecting. You got to go into this special thing and tell it to disconnect and reconnect again because it's a bug in the system. I do it. Sure enough, it's all fine. Anyway, it's just funny. Technology's funny, huh? There's some bug in the programming. Anyway, it's great to have Google. I appreciate Google. They answer everything, almost. All right, so here we go. So this is, they're trying to, city planning, they're thinking about doing some kind of thing where they're going to revitalize the town mall. They're going to revitalize the town mall. Interviewers are asked to pick a street corner, blah, blah, blah. Ask people if, they're going to spend public funds, right? So they're going to spend, I wish they'd ask me before they spend public money, the money that my tax dollars contribute to. So I guess they do sometimes. So spend public funds to revitalize. So they're going to ask, should we do that with public money? Should we revitalize the mall? So they had a bunch of interviewers go out. Interviewer A, 33 people said yes, 67 said no, 323 didn't respond. They just kept walking, right? They tried to ask them, hey, should we? And they just, I don't got time for that, right? And they just kept walking. Get the idea? And then B, etc. So there's the results. And notice everybody asked 100 people, right? 33 and 67, that's 100. Not asked 100. They got 100 responses. Yeses and nos. They kept asking until they had 100 responses except for E. E only got, 64 responses and got tired. That's what the little note is. Got frustrated and quit. So E quit because E had 590 people keep on walking. I don't know what's up with E, but they didn't want to talk to E. So everybody else had 100. You tracking with me? Yes, if you add up yeses and nos, see right there, 20 and 80, that's 100. 80 and 20 is 100. 57, 40, so they're all adding up to 100 except for E. So, and then the whole bunch of non-respondents. So they kept track, trying to figure out, hey, do the people want us to spend public money to revitalize the city? Let's think about this kind of a survey. What size was the sample? 464. So what I did for that is I just added up. But it's easy to add up. Remember, A's 100, B's 100. C's 100, D's 100, and this one is 64. If you just add up 12 and 52, It's 64. So that adds up to 464 for the survey. B, excuse me. Calculate the response rate of this survey. Was the survey subject to non-response bias? Response rate. Yeah, that's on your sheet, but let me give you the definition. Response rate is number that responded over total number asked. The number that responded over total number asked. So how many actually responded? Well, 464, right? That's what we have. 464 said either yes or no. How many altogether were asked? How many altogether were asked whether, asked something? All these people did not respond, did they? So we have to add up those numbers. What's the total of all those numbers? I have no idea. So if you add all those up, I'll do them right here. 323, 212, 105, 85, 590, 10, 15, 17, 18, 20, 21, 5, 6, 7, 8, 13, 13, 15. Those are non-respondents. So you got to take 13, 15, and you got to add the 464 who did respond. You with me? To get the total number that were asked. How we doing? Is this making any sense? To get response rate, again, it's what percentage responded. It's what percentage responded. So it's the number that responded over the total number that were asked. 464 responded. Over 1315 did not respond. 464 did, so this is the total number asked, whatever this is. 1779. 1779. So if you divide 464 by 1779, I guess you get, can somebody verify, is that right? You get 26.1%? Does that seem somewhat reasonable? Yeah, that looks close to me. I'm looking at it. Yeah, good. So that's how they're doing this. Does that make sense? Response rate. Response rate. And so then, why do we care about that? Like, what a dumb thing. Who cares about the people that didn't respond? They didn't respond. Well, actually, there's something called non-response bias. That's actually a bias. And yes, this survey suffers from non-response. In other words, most people did not respond, right? They had a really low, only 26% of the people that were asked gave an answer. So we don't know what the other 74% of the people even think. Now, why does that matter? Again, why does that matter? Who cares? They didn't respond. Well, what that means is, it's kind of like, if you guys have you seen, this is the most common mistake done in society all the time, as far as a faulty sample. They'll tell you, all right, call into this phone and radio station. They'll go, call into this number and let us know what you think about whatever, this issue, right, or this person or whatever. And so people will call in and give their opinion, and then the radio show later will say, 72% of our callers, think this issue is great or terrible, or this person is great or terrible, or whatever, right? Or you'll see online, like somebody will say, you'll be watching sports or some other kind of thing, and it'll say, text into this number your opinion of this issue, and a whole bunch of people will text in, right? And then they'll give the statistics. 29% of people, you should not believe those. Those are, what I mean believe, they're not telling the truth. That's not really it's not really true that 29% of the general population feel that way. If they did polling that way, they would not get anywhere near the truth of what really will happen when the actual election is handled. Why? Because when you have a lot of people, when you set up your polling in a method where a lot of people don't respond, you end up only getting the people that are highly interested in the topic responding, which is a different kind of animal, so to speak, than the average person. Do you see what I mean? For example, if I'm asked, you know, those calls that call and they say, will you give us this information, that information? I never. I don't. I don't care that much. I don't care a lot. But some people, like if it's a sports thing or something like that, they just care a whole bunch, and so they respond about who their favorite basketball player is, or who their this is, or who their that is. Well, those are the diehards. Those are the people that really love it. So they're going to call in, they're going to text in. Well, yeah, so you're getting the opinion of the diehards, but you're not getting the opinion of the average person. That's called non-response bias. It biases your results. It gets you faulty information. You're not really getting the true percentage of all people that feel that way. Does that make sense? If you try to predict a national election that way, you'll be sorely disappointed. You'll get false information. And that's a lesson they learned throughout history. We'll talk about it as time allows. Is that good? Does that make sense? You stop me if you. All right. Study was conducted to determine how many undergraduates at a university are familiar with a new financial aid program. Too many students to conduct census. Following sample method is used. Blah, blah, blah. Okay, what they do is they pick a number from 1 to 100. They count that far down the list. They take that name, and then they take every 100th name after it. That's a sampling method. That's weird. All right. So explain why the method used for it's not simple random sampling. So that's random sampling, but it's not simple random sampling. Why not? Well, because you're going to get a gap of 100 between all your choices. Did you understand what they said? Did I read that too quick? They're going to take a list of thousands of names, and they're going to randomly pick a number from 1 to 100 and go down and start there. Start at, whatever, some name. Boyd. They're going to start at Boyd, B. And then they're going to add 100. Add 100, add 100, add 100, just keep randomly picking names. Well, that's a form of random sampling, but it's not simple. Here's the reason why. In simple random, any two members have as much chance of being selected. You could pick two names right next to each other if it was simple random. That'll never happen with this style of random selection. Do you see the difference? Simple random means just take all the names, kind of like put them in a hat and just pick them out at random, or have a computer randomly generate numbers. That's called simple random. This is random, but it's a different kind of random where you're not going to get two names right next to each other because you're jumping 100 every time. So that's all. It's kind of a silly point. It's not that important. I probably don't even put that on the test. B, if 100% of the respondents claim they were not familiar with the new financial program offered by the university, is the result more likely due to sampling variability or sampling bias? Yeah, there's no bias here. It's just sampling variability. The students appear to be representative. Yeah, it's just random. So that's what they'll be asking you about. Is there a bias in this one? So if they'd asked me that question on the last one with the surveying the street corner, whether you want to spend the public money, that would be biased results. Why? Because so many did not respond. So that's a biased study. You're only getting the opinion of those really interested because they're willing to stop and answer your question. So you have to design studies in a way where you get most people to answer. Otherwise, you're getting biased results. Is that making sense? Not getting to the truth. All right, so this section is going to have more calculation. How do you count how many fish in a lake? It seems like, where'd that come from all of a sudden? What does that have to do with collecting statistical data? How do you count? Here, let me get off this screen, which is confusing. Let me just ask, how do you count the number of fish in a lake? Really, seriously, does anybody know? How do you count the number of fish in a lake? How do they do that? Biologists do that. They estimate. They don't count every single one. Tell the fish to count off. 1, 2, 3. What do they do? Because that could be tricky, right? Even with technology, even if they use like sonar and the boats like go over it and they see the little blips moving around, that's not going to work so well. Especially if you want to distinguish like trout from bass or something like that. They use ratios. They use math, actually. It's like surveying the fish. That's why it's in this section. Here's what they do. They do what's called catch, tag, and release. Catch, tag, and release. They do this for all kinds of for counting rabbits in the field or deer in the mountain. It's critters. This is what they do to count critters. They catch, tag, and release. So let me give you the feel first off, because it's always best in math if it feels right, and then I'll give you the particular formula. So suppose, just real life, suppose we catch, tag, and release 100 fish. All right, and then 1 week later, so you throw a big net down, you pull up 100 fish, you put a little tag on all of them, you let them go, they swim around again. 1 week later, you catch at random, so here's the random sampling. It's just like sampling, same concept. You catch at random, I don't know, let's say 50 fish. And you find that 25 of them have tags from last week. From last week like that. So, think about what that means for a second. So, you catch a bunch of fish, 100, you put tags on them, you put them back in the water, and a week later, you catch 50 and find that 25 have tags. Does that give you any guess as to how many fish are in the lake? Think about it for a second. This last part is like polling. It's like if I went out and I asked who you're going to vote for the governor, and 25 out of 50 people said they're going to vote for Joe Blow in the next governor election. That's half, right? So I would think, maybe half of the whole state is going to vote for Joe Blow. It might not be a perfect sample. We'll get into all that. Stepping aside from all that stuff for just a minute, just thinking about fractions, that'd be a half, right? So if I asked 50 people at random, who are you going to vote for, and they said Joe Blow, 25 of them did, I would think, half of my little sample said they were going to vote for Joe Blow. Maybe, if that's a good study I did, then maybe that's a half of the whole state is going to vote for Joe Blow. That's what we're doing with the fish, right? If we grabbed 50 fish a week later, and half of them had tags that we'd put on the week before, then we would think, I just grabbed these at random, and half of my little group had tags, and since that's random, probably half of the whole lake out there has tags. That makes sense, right? Just like polling, you just assume whatever happened in your little sample is representative of the whole population. So, if that's true, if half of your little sample has tags, you would think, it would be natural and right to think, well, probably about half of the entire lake is tagged fish, right? Because I just grabbed some at random, and 25 out of 50, half of them were tagged fish. So probably half of the whole lake. If I put these back and grabbed a chunk more, I'd find about half of them are tagged every time. So probably half of the whole lake is tagged fish, and you know how many have tags because you did it the week before. You tagged 100. So if half of the whole lake probably is tagged fish, and there's 100 tagged fish, then how many are about in the lake? About 200. Do you see that? Because that would be half, 100 out of 200. Do you see how I came to that conclusion? Right? Because if half of your sample is tagged fish, then probably half the whole lake is. Because you just grabbed those at random and looked them over, right? Said, half the fish in my sample were tagged. Probably half of the entire lake is tagged fish. And I know how many have tags, 100. So that's probably half the whole lake. So there's probably 200 in the lake. See how that leads you naturally to an estimate for how many fish are in the entire lake? So that's the concept. How do we do that? Tag over total equals tag over total. That's and this is for the first catch, and this is for the second catch. So that's the formula we use for estimating. That's what biologists really do for estimating fish or deer or rabbits. They catch, tag, and release. So the first catch, tag over total, equals the second catch, tag over total. So let's go back to the problem then. If you got that written down, I'll bring it over here and bring back the problem. Okay, so first catch, tag over total, equals second catch, tag over total. Okay, so what do we got there? So let's suppose that you first capture 500 fish, tag them, and throw them back in the pond. So 500 fish, so that goes right here, huh? That's the tagged number in the first catch. We tag them all and catch them. Catch them all and tag them. And then after a couple days, so now we're going to second catch, right? Second catch, couple days, that's just to let them mix around, rank at random, just like surveying. You go back and capture 189, of which 27 are tagged. You find 27 tagged out of 189 in the second catch when you grab them and look them over. Does that make sense right there? So call this one X, right? We have 3 out of 4 numbers. Call this one X. And then we have an equation. We have 500 over X is 27 over 189. Bless you. Everybody see that? See what I did there? So again, 500 were tagged in the first catch. And in the second catch, there were 27 tagged out of 189. Call this one X. Now, how do we solve? X will be the total that we're looking for. We just got to solve this equation for X now. How do we solve? Like when you got 2 equal fractions? Do you remember ever doing that kind of thing in algebra? What you can do to solve that? But, yeah, I think that's the easiest way. There's other ways too. Yeah, I think cross multiplying is real nice. Just cross multiply. 500 times 189 is 27 times X, like that. Is it 94,500? Yeah. 94,500 equals 27X. And how do you finish solving for X there? Divide by that 27. What's that come out to be? Oh, the answer? 3,500, huh? Is that good? That did come out 3,500, right? Yeah. Is that good on that? Does that make sense? That's a way to estimate the number of fish in the lake. Yeah. Exactly. Yeah. Right. Because those 500 fish are tagged. Yeah. Exactly. So that's a tagged when it goes on top, and then over here the 27 are tagged, so it's top. The 189 is total for the second catch. Yeah. Is that good? Easy enough on that? Good, good, good. Okay. Let's try. Have us do it again with coins. Okay. A lot of words there. Blah, 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 blah. Basically, you have a big jar full of nickels, dimes, and quarters. Nickels, dimes, and quarters. You don't want to count. It's like gigantic, so you don't want to count them all, but you want to estimate how much money you have in there. So what you decide to use the capture recapture method. That's what I call it, catch, tag, and release. It's capture recapture is what they also call it. For the first sample, you shake the jar well, you draw 150 coins, and there's what you get. So let's write that, 150 coins, and you get 37 quarters, 45 nickels, 68 dimes. That's like the first catch. Using a black marker, you mark the 150 coins. You mark them. That's like tagging them. Does that make sense? It's like we're tagging the fish, we're marking the coins. So we just reached in at random, grabbed a bunch of coins, like grabbed a bunch of fish, mark them all, put them back in there, mix it all around, like giving the fish a couple days to mix all around, right? And then later, shake and then you get 100. You pull out 100 coins. Coins. And what you find when you do the 100 coins is you get 35 quarters. 5 have dots. You get 28 nickels. 8 have the black dots, the marks. 37 dimes. And 14 have dots on them. Estimate the number of quarters in the jar. Okay, so all they really, I shouldn't have written all that stuff down about dimes and nickels, because all we care about on this one is the quarters. So, number of quarters. How do we do it? Tag over total equals tag over total. Tag over total is tag over total. Tag over total equals tag over total. Okay. So, how do we go from there? So for this is the first catch, the second catch. So in the first catch, how many quarters did we tag? Yeah, that's it, on the 37. So there it is. That's the 37. That's the tagged number. In the second catch, the 100 coins, there were 5 tagged out of 35. And this is our X. Does that make sense? See how I came up with that information for the quarters? Everybody see that? So, again, for the first catch, we took 37 quarters and we tagged all of them. They said we marked all those ones we got out the first time. So 37 tagged, 37 marked. And then the second catch, after we mixed them up and grabbed 100 out, we got 5 marked, 5 tagged out of 35 for the second catch. And so then here's our X, just like the last one. Cross multiply and solve for X. Is that good? Just go diagonal, 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 diagonal. So we get 37 times 35 is 5X, like that. Remember that cross multiplying from algebra? Diagonal, diagonal. And what is 37 times 35? 1295. Thank you. 1295 is 5X. Last step, divide by 5. X equals, and that's the 259 number that's right here. So we're estimating that there's 259 quarters in there. How are we doing? Is that making any sense? Do you see how that works? It's kind of weird, huh? It's a way of estimating how many quarters in the jar without actually counting them all. It's pretty accurate. It's not exact, but it's approximate, but it's pretty accurate. It's all based on marking some of them, letting them go, grabbing out a new random sample, and based on the proportion that are marked, you realize that's the proportion for the whole jar. And you can get an estimate on the whole jar that way. It's a tricky little maneuver, tricky little use of math. So you know how you can figure out how much money's in that thing, right? Because 250 quarters times 25 cents each, whatever that's worth. Questions on that? Is that good? So whenever you do these tag ones, it's tag over total equals tag over total. That's the formula. So you want to put that in your 3x5 card for our next exam, which is next Thursday, huh? A week from today. A week from today is exam number 4. Okay, I'll keep moving. No questions. Can you read that? It's a lot of words all of a sudden, huh? I don't think you probably want to write all that down. So, well, you have it on your screen. It's number 5, right? When you go on the Math Excel homework, it's going to be the same words. They might change the numbers a little bit, but probably not. It's probably exactly the same. All right. So, what's going on in this question? There's some new vitamin decides to sponsor a study to determine the vitamin's effectiveness in curing the common cold. So, if they're going to do a study, be thinking about what are those drugs that they say or help the cold? What is it? There's 2 big ones on the market now, right? I can't remember what they're called now. Yeah. Is it Airborne? Yeah. Isn't that one of them? Yeah. Airborne. And it starts with a Z. What's the other one? What is it? I don't think so. Anyway, there's a couple of them. Anyway, and if you read the fine print close, they say have not been scientifically proven to help, but many people think they do help the cold, right? That's what they say. Well, we'll see why here. What it would take to scientifically prove. We'll get into some of that right here. Okay, so all right. So what they're trying to do is they're trying to prove if the vitamin is effective for curing the common cold. All right. So you guys be critical observers of the study. See if you can start to gain those skills. 500 out of the 50,000 college students in a large city were paid to participate as subjects in the study. Okay, so 500 out of 50,000 college students, large city, were paid to participate in the study. All the participating subjects were suffering from a cold at the start of the study. The subjects were each given 2 tablets of vitamin X, whatever it is, a day, based on information provided by the subjects, themselves. 457 out of the 500 were cured of their colds within 3 days. The average number of days a cold lasts is 4.87 days, so that's quicker. So it's helping them get over their colds quicker. Okay. As a result of the study, the manufacturer launched an advertising campaign based on the claim that vitamin X is more than 90% effective in curing the common cold. Where are they getting the 90% thing? Yeah, good, well said. Yeah, if you take 457 divided by 500, it'll be 90.91 or just over 90%. So they're saying, hey, look, 457 out of 500 of the people in the study we did were shortened their cold early, right, by a day or 2 days or something. Okay. So what do you think about that study? What do you think about the merits of that study? Any problems? Let's be critical observers. Any problems with that study? Is it a good study? Do you believe it? What do you think? Yeah.
Because some of them were paid and the others weren't.
Good point. Yeah, really good point. Yeah, they're paid. Yeah, all the people that were in this study anyway were paid. So yeah, if the company's paying you money, do you think that might tend to have an effect? You're like, yeah, I feel great. Your medicine's working great, right? To kind of overemphasize the effectiveness of the medication because they're paying you. Yeah, that's a huge problem. That's one. Good. Well, and that's probably the biggest. That's really, really, really bad to pay people and then expect to get the truth, right? We're trying to get the truth here, right? Remember, the goal is to find the truth on whether this vitamin really does help or not. And if you want the truth, you don't pay the people. If you want to lie so you can sell the stuff, then you pay the people. But if you really are interested in truth, then you don't pay the people, because that'll twist the truth. Okay, what else? That's a good observation. Other observations? Anything else? Any other problems you can see with it? Well, how about we go down to the questions? Maybe some things will come out. Question A, choose the correct terms. Yeah, control group. Yeah, so we better talk about some of the terms. We're getting ahead of ourselves, I guess, with this example. Let me help you. We're going into what's called now clinical studies, like medical kind of things. Like, how do they determine if drugs or surgeries really work? How do they do that? Well, there's a bunch of different things they do. They're all the terms are written out in your sheet for you. Let me go over here and just mention a couple of them. What's it called? I guess it's on the back. Yeah, we're on the back. So all the clinical stuff is on the back side. We're on the back now. So clinical study trying to determine if a single variable or treatment can cause a certain effect. Oh yeah, confounding variable is a problem. Okay, yeah. Let's talk about what a controlled study is. A controlled study, it's written there on your sheet. You got to have two groups. You got to have two groups. You got to have a treatment group and a control group. To have a controlled study, you got to have a treatment group and a control group. Maybe it'd be helpful at this point if I threw out some information, real life kind of information. Did you guys know that if you take all the people in the world who drink milk, or at least have had milk at least once in their life, versus all those that haven't. So I take the world. Here's the world. Here's the whole world. And I'll take over here the people that have never had milk. And over here, this is had milk at least one time in their life. Okay, if you break the whole world up into two groups, one that has never had milk in their life, and the other group that's had it at least once, what you'll find is this group, this is true, I'm not making this up, this group that's had milk at least once in their life, they die of cancer much more than the other group does. The other group doesn't die of cancer nearly as much. That's true. I'm not making that up. So, right, you get what I'm saying. Those that drink milk, at least have had it at least once. So I'm talking about, even if you're lactose intolerant, even if you don't drink milk regularly, if you've had it at least once in your life, then you're in this group, had it at least once, those people die of cancer much more than that other group that have never had milk even once in their life. So, milk causes cancer. Let's clear the shelves. No. But it looks that way at first. This is true. What I'm showing you is true. Then why does nobody care? Why is this true but unimportant? It looks important. You kidding me? People that have had milk at least once, they die of cancer way more than the people that have never had milk once in their life. I mean, way more. The numbers, I don't know what they are, but I'm sure they're huge. Well, so the milk's causing cancer. No. That's not a controlled study. Why? And I don't just need to use verbiage. There's something really uncareful, unscientific about that information. But people present information that way all the time. This is where you want to be a wise consumer. What's going on there, first off? Why is that the case, and yet milk is not causing cancer? How can that be the case, and yet milk is not a causing agent of cancer, or have anything to do with causing cancer? Anybody have any idea? It's like a mystery, huh? How can that be true and milk not cause cancer? Well, what it is there's another variable. They call it a lurking variable. It's hiding, right? Lurking is hiding. There's a lurking, which means hiding, variable. There's something else going on there behind the scenes. Think about this group for a minute. Never had milk even once in their life. I bet you've all had milk at least once in your life. I bet almost every single person in Fresno County has had milk at least once. Maybe there's one or two, but almost everybody's had milk at least once, right? At least once. Formula when they're a baby, or some kind of milk at least once in their life. Who is it in the world this is a rare group that's never had milk at least once in their life? Are there people in the world like that? Yeah. What's up with those people? Not only have they not had milk, they haven't had basic nutrition at all. They live in some third world country. Their nutrition, they're in poverty, right? They're impoverished. That's why they've never had milk even once in their life. They're impoverished. They don't have milk. They don't have vitamins. They don't have food, right? They're like, what is it? A child dies every day? No, not every day. Every day. That was a silly statement. A child dies, what is it? 23,000 children die every day. Isn't that what it is? Every second or something like that? You know, around the world because of simple poverty needs, right? Was it? Yeah, half a stadium every day. 23,000, like half of a football field. Every day because of simple, impoverished needs around the world. 23,000 today, right? Because they don't have basic food and medicine and things like that. So, you get it? They never have a chance to die of cancer. They don't get old enough to die of cancer. They never have a chance for that. They die of malnutrition at 1 year old or something like that. They're among the 23,000 that die every day in our world, not here in Fresno County. Even though we think of ourselves as poor, we know nothing compared to the world scene and what the world means by poor. There's a whole different scale. So anyway, right? So do you see how it's tricky? It's not that milk is causing cancer. If you drink milk, you're more of a regular person and probably have more regular diet and have a chance to get older and have a chance to die of cancer. So yeah, you die of cancer more frequently, but it's not because the milk is causing you to die. The milk is giving you life. Milk and all the other nutrition that goes with it is giving you life. So you live longer and then you have a chance to die of cancer. It's very reasonable once you see it that way. The lurking variable is poverty or malnutrition. Probably would be the better way to say it. Malnutrition. It's malnutrition that's making this group die young and never have a chance to get cancer. Make sense on that? Do you see the difference? You see how things can look confusing at first? Let me give you one more. If you take all the states, let me do one more over here. If you take, the United States, I was going to try to draw it, it won't work. Let's take the United States. And you take each, whoops, that's an in there. The United States. And you go state by state, California, Texas, New York City, Vermont. How do you Vermont? VM? I don't know, whatever. On you go. Take all the states, right? If you take the states that have more Boy Scouts, the states that have more Boy Scouts, some states have more Boy Scouts than others, then 20 years later, that state, or those states, I should say those states have more criminals locked up in the jails. That's true. Again, I'm telling you something is true, but it doesn't mean what it appears to mean. See by the way, how easy it is to lie with statistics? Have you heard that saying before, that it's easy to lie with statistics? This is what they mean. So easy. So easy. You want to make somebody think a certain thing? You just throw out some information. You're not lying. You're just throwing out the information. No, you're lying. If your aim is to deceive, then that's called lying, however you do it. But anyway, they say they're not lying, but they do this all the time in our information age, right? They do things like, now that's true. I'm giving you true facts, but it looks like the Boy Scouts are cranking out criminals, aren't they, right? The states that have more Boy Scouts, 20 years later, they got more criminals. No, the Boy Scouts are not cranking out criminals. But how can this still be true, and yet the Boy Scouts are not producing criminals? What's going on? How is that true? The states that have more Boy Scouts 20 years later have more criminals. Quite a bit more. I mean, the numbers would bear it out. If we could ask Google, are these numbers true? Google would say, yep, those numbers are true. If there's some kind of statistical thing. I like things like that. I like to just know the truth. Boom. That's the truth. Yet, Boy Scouts are not cranking out criminals. Why not? There's a lurking variable. There's a variable that's hiding. Something else is doing the causation. Do you see what I'm saying here? Association is not necessarily causation. That's what we're seeing in these two examples with the milk cancer and the Boy Scouts in the States. Just because two things are connected doesn't mean one is causing the other. Just because milk and cancer are connected, they're connected by malnutrition. Doesn't mean milk is causing cancer, right? Boy Scouts are now why? Why is this true? We still haven't answered why this is true. Why would states that have more Boy Scouts 20 years later have more criminals? Let's talk about California in particular. Do you think California has more Boy Scouts than other states? Yeah, California has more people than other states. So California's got more Boy Scouts. California's got more Girl Scouts. California's got more Little League baseball players. California's got more softball players. California's got more everything because we got more people. So yes, we have more Boy Scouts, and yes, we have more criminals. We've just simply got more people. Do you see? It's the underlying, the lurking variable here is population. That's all. That's all that's going on. It looks so deceiving at first, didn't it? Yeah, the states that have more people have more everything. They have more Boy Scouts, they have more criminals, they have more honest people, they have more everything. They just have more, right? You see how it looked confusing at first? But the lurking variable's population. So the point is you've got to be careful when it comes to statistics and information that's reported to you. And people try to conclude causation when it's not necessarily a causing kind of thing. Okay, well then that begs the question, how do you know when something does cause something? Because you need to know, right? There are things that cause cancer. Smoking does cause cancer. That's been well determined, right? How do they know? Well, they've done controlled studies, haven't they? They've done, and so now let's talk about how do you prove one thing is really causing another? If you've got to be so careful all the time about being connected doesn't mean causation. How do you prove it? Well, you do what's called a controlled study, as I mentioned a minute ago. So let's get down to it now. So those were the two examples that don't do that. So, but how do you prove it does? Controlled study. You have a control group and a treatment group. What am I talking about? The control group gets the placebo. What is the placebo? Anybody know? What's a placebo?
It's like a product that said have an effect but really doesn't.
Yeah, it's like a sugar pill. Yeah, it's false. It's right. It's like a sugar pill. It's not real. In other words, so and whereas the treatment group gets the real drug, whatever it is, the real antibiotic, the real medication, whatever it is, right? So the way you determine if the scientific method for determining if something is really causing something is a controlled study where you have two groups. You got to break them up. You got to have a control group that gets the fake drug and the treatment group that gets treated. They get the real drug. And then you compare results. Why? Why do we split them up and do that? Why do we give people a sugar pill? Why don't we just give them nothing? First off, do you understand why we split them up? We split them up because the only difference between these groups then, everything else is the same. You make sure that you randomly break people into these two groups so that the only difference between them is some are getting the treatment and some are not. So any differences that you find in the results must be due to the drug because that's the only difference between them. That was the problem with those other studies I gave you, right? The Boy Scouts, they weren't equal groups. There was California and then there was Vermont. We have a lot more people. That wasn't an equal group to compare. Same thing with the milk drinkers, the non-milk drinkers. Those are not equal groups to compare. But in a controlled study, you've got to have totally equal groups. Groups that are the same in every way, except one gets the drug, one does not. That way you know any differences are due to the drug. Now, what's a placebo? Well, I already said sugar pill. Why do we give people a placebo? Why do we do that? Why give anybody a placebo?
To see if the results are accurate.
Why would that help us see if the results are accurate?
Just to see if I guess the reactions are accurate, because you could give someone a placebo and they might feel like something's happening, and with the real drug, something might actually be happening.
Right. Yeah. And not only feel, but sometimes things actually do happen. Right? Science has proven a lot in the last 50 years that our minds have a huge effect on our bodies. We're not just physical, we're mental, right? Everybody is common knowledge now, right? They weren't sure about that 50 years ago, but it's pretty common knowledge now that if you think something's going to help you, your mind can have an effect on your body. And so they want to know, hey, Is it just mental? Are people just thinking they're getting a good treatment, so that's what's making them better? Or is it the actual drug doing something physical that's helpful? That's how they distinguish that out. They give the false bill. They tell them, you're getting the drug, and they're really not getting the drug to half of them. So they'll think they're getting the drug, and the other people are really getting the drug. That way, if there's any difference in results, they know it's the actual drug making the difference, causing something. That's how you scientifically determine causation. There's also a couple things you gotta be careful with in these studies. A lot of times it's medical, and the doctors are examining people to see if they're getting better from the measles or the polio or whatever. And that was another problem with the other study. Like if you self-report, remember the study, we're going to go back to it in a minute, where they took the vitamin X, and they reported themselves they were better. Well, that's part of the deal. You don't let people report themselves, because they're going to be skewed. You let a doctor come in and examine them to determine that. And part of what you do is you blindfold the doctor. I don't mean you really put a blindfold on him, but you have a blind study. And that's written down on your list of things as well. So in other words, you don't let the doctor know which patients received the real treatment and which ones just got the sugar pill. You don't even tell the doc. You have some administrator over the thing. Actually, that's called double blind, when you don't tell the doc and you don't tell the people, right? Obviously, you don't tell the people, hey, you're just getting the sugar pill. You don't tell them, right? Because that would wreck it. So you let them be blind. They're blind as to whether they're getting the real drug or the sugar pill. And you also don't even tell the doctor sometimes. You have an administrator over the whole experiment, and you don't even tell the doctor, because it's a close call. Sometimes, have the measles gotten better? There's a couple of bumps, but is that better? Sometimes it's a close call for doctors. And if they know, this is somebody that was really given the drug, they might tend to skew, I think that's getting better. Or if they know, no, this person, it was a fake thing. No, they still got the measles. They might not be as truthful as they could be. So even the doctor sometimes doesn't know. That way you get the best results in a double-blind study. This is exactly, by the way, how they wiped out polio. You guys know about the history on that? I always like history. I think it's history. 1954, the Salk polio vaccine. That's exact. Yes. Ankle surgery. You've got one like this in my thing here. Yeah. Let me read this one. This one always cracks me up. It's just like this. It's basically this question here. This one goes, there was a clinical study done at Houston Veterans Administration Medical Center on the effectiveness of knee surgery. This is real. This isn't made up. They did this. It was in Houston. It's a Houston Veteran Hospital. And 324 individuals who met the inclusion criteria for the study, 144 declined to participate. The researchers randomly divided the remaining 180 into three groups. One group, so they took, this Houston, let me here, I can just write it right here. So in this Houston VA hospital, Veterans Hospital, what they did is they took 180 people who needed knee surgery. So now they're testing, does the surgery really work? Okay. 180 people. They broke them into three groups. First group, randomly. So they randomly broke them into three groups. First group got one type of surgery, arthroscopic knee surgery, called debridement. So you got the second group. So the first group got the debridement kind, whatever that is. I have no idea. You probably don't either. Some kind of debridement, knee surgery. The second group got a lavage, whatever that is, kind of surgery. And the third group, this is the interesting part. The third group, skin incision, no actual surgery. It's like a sugar pill, right? They cut them open for nothing. They cut open their knee, made a skin incision, patched it up, said you had the surgery. They all knew it going in. The 180 were part of the study. That's why a bunch declined. How many was it? 144. Originally there was 324 original. 144 declined. I might have too, right? If you came in, they said, all right, we're setting up this study. We want to learn if the surgery is really working. You want to be part of it? 1/3 of you are not going to get the actual surgery. You won't know, right? Because they want it to be blind, right? Not double blind. The doctor's not blinded. That'd be a problem. But just blind, not double blind, right? You're gonna. You see why a lot of people said no, thank you. I want real surgery. I don't want fake surgery. But 180 agreed, and 60 of them were in the group that just got cut open and no surgery done. Well, anyway, afterwards they asked them all. This was really done. How they felt. Where is it? The patients in the study did not know which group they were in, and in particular did not know if they were receiving the real surgery or simulated surgery. All the patients who participated in the study were evaluated for 2 years after the procedure. They didn't tell them for a long time. For 2 years, they kept being evaluated, said, how's your knee doing? Is it getting better? Is it better than it was? All that kind of stuff. For all the groups, for all the groups, they asked them for 2 years. In the 2-year follow-up, all 3 groups said they had slightly less pain, all 3 groups, and better knee movement, all 3 groups. But the group that reported the best results, guess which group?
The last one.
The last one. They reported the best results. What does that mean about the surgery? It's doing nothing, which is important to find out and quit doing it. Do you realize that? It's all mental. That proves it's all mental. The people that got nothing felt just as good as the people, even better, than the people that actually did something. See, that's an important result. Then they go, this surgery's doing nothing. That's the hunch the doctors had. That's why they did the study. You might think, well, it's a waste, those 60 people. Well, how about all the people they've been operating on all over the years, and it's all for nothing? So they had to change their style of surgery, or they learned from that really the surgery was doing nothing. That was an actual study done in Houston VA Hospital. So that's an interesting result. So coming down here, this is pretty much what this thing is describing right here, right? Some kind of one group receives type A ankle surgery. The second group, type B ankle surgery. The third group, skin incision to make it look like they had surgery, no surgery, da-da-da. Choose. Okay, so what are their questions? I can't even tell what their questions are. They're saying describe the target population. What is their target? What are they aiming the arrow at? What are they wanting to figure out? All potential ankle surgery patients, right? Isn't that the goal? Do you guys understand that? And this kind of question fools a lot of students, I think, into saying, well, it's the 159 or it's the 324. No. Really, why are they doing this? Why did the Houston VA do that? They didn't just want to help those people. They wanted to help all people in the future who would perhaps need knee surgery, and whether this would be helpful surgery or not, right? That's their target. That's their goal. So it's all potential ankle surgery, or in this case, or knee surgery for the Houston one, patients, right? That good? You won't be fooled by that? Nobody will be fooled by that now, that kind of question, I hope. A little bit of time here. You've got the ideas now. So, okay. Knee surgery, researchers, one group, so same kind of thing. One group received type 1 surgery. Second group received different kind of surgery. Third group, skin incision, same kind of thing. All right, let's go through the questions. What's their question? Well, it looks like the screen's not rolled well. Okay, here it is. Was this study a controlled placebo experiment? Yes, right? Everybody able to answer that? There was a control group receiving a fake surgery. Placebo is a fake. A placebo is a fake. So there was a fake group. And that's what you need for control, right? They didn't get the actual treatment. They didn't get the actual surgery. Like not getting a drug, not getting a surgery, same thing, right? That is a controlled study, and it's a placebo experiment. A fake. There's a fake. Yes. B, describe the treatment group in the study. The first treatment group consisted of those patients A. The second was type B. Those are the ones who got treatment, right? That's the treatment group. Yeah, the rest of the options, I'm trying to read the other ones. They're silly. They're silly. Okay, C. Could this study be considered a randomized controlled experiment? Yes, the 150 patients were assigned to treatment group random. Yeah, it was done at random. If you read up here in the words, 150 patients in the researcher randomly divided. Why is it important to randomly divide the people? Why does that matter so much that it's random? What if the doctor what if they just, hey doc, you just pick some and they'll be in this kind of surgery, and pick some other ones and then pick the fake ones. You just pick them. You know, whenever humans get involved like that, whenever there's something other than random, we tend to do a certain thing that throws off truth. You know what I mean? The doctor might think all the patients that look like they're going to be healed well and give them a certain kind of surgery, and other ones a different kind. I don't know, different doctors do different things. But the point is, remember what we're trying to get at. We're trying to get at the truth of whether these surgeries really do something. And so to do that, you can't have any other differences between the patients. So random keeps that pure. If it's random, then it's random. And there's nothing different about this group from that group. Whereas if you have a doctor pick them, well, these are going to be the ones that Dr. Jones picked, and these are the ones he didn't. And these are the, and that's different. Then there's probably something different about those people. And something different other than the surgery, right? And you want the only difference to be the surgery or the drug or the whatever. That's why it's so important that you do random and that you have a controlled group, because you're trying to isolate. You want to make sure you don't make the Boy Scouts criminals mistake, the milk cancer mistake. And the way to avoid those mistakes is to have nothing else different between the groups except the treatment. And to do that, you just randomly. That's what they did with the polio. They just random. That's why 338,000 kids declined, because they told the parents half of them are not getting the drug for the next 2 years. How would you feel if your kid had polio? And they said, you want to do this experiment? Not going to get the drug for 2 years. Maybe. Won't know, right? That's why a lot said, no thanks. And they declined, right? So then they just rolled dice or whatever, randomly broke them, because that way there's no distinction other than the drug between the groups. Was this experiment blind, double blind, or neither? Why is it blind and not double blind? What does that mean? Blind and not double blind. The answer is blind. You can see it checked there. What's the difference between blind and double blind? Who in a blind experiment, who's blind? Who's blind means not know. They're not in the know. The subjects, the patients, right? So the polio thing, right? The kids did not know, and their parents did not know whether they were getting the real thing or not till 2 years later or whatever, right? This was a double blind, because not only in the polio Salk vaccine trials of 1954, not only were the patients blind, but also the doctors. Doctors were also blind, meaning, I don't mean they're blindfolded, but the doctors weren't told which kids got the polio vaccine and which ones didn't, because it's a bit subjective. They would examine a kid and they go, does he have the polio? Does he not? And it's a little bit subjective. So they didn't want the doctors to know which ones had been given the real drug and which ones had not. Administrators above knew that, but the doctors did not. Now, and this one we're doing right here, this neck surgery thing. Do you see now why it's blind and not double blind? It's not double blind, because the doctors know. Obviously, they're doing surgery, so they know whether they gave a real surgery to somebody or didn't, right? Does that make sense? So it was not double blind. That would be dangerous to blindfold the doctors during surgery. All right, so it's not double blind. Okay, it's all describing some big experiment. All right, following excerpt refers to a landmark study in 1896 in Denmark by Dr. Johannes Fibiger, who went on to receive Nobel Prize in Medicine in 26. The purpose of the study was to determine the effectiveness of a new serum for treating diphtheria, a common and often deadly respiratory disease in those days. Fibiger conducted this study over a one-year period in one particular Copenhagen hospital. New diphtheria patients admitted to the hospital received different treatments based on the day of admission. In one set of days, call them even days for convenience, the patients were treated with the serum daily and also received the standard treatment. Patients admitted on other days, odd days, received just the standard. They didn't get the serum. Over the 1 year period, 8 out of the 239 patients admitted on the even days and treated with the serum died, whereas 30, many more died on the odd days. See that? Only 8 died here. 8 died who got the serum, and 30 died without. So it seems like that's pretty good results. I mean, that's almost 4 times as many, right? 4 times 8, 32. So it's almost 4 times as many. So the serum's making a difference. Clearly, then we know the serum is doing the deal. See how he did it random, this doctor? He just said, oh, let's do even days. When they come into the hospital, if it's a Monday, they're getting the serum. If it's a Tuesday, they're not. If it's a Wednesday, they are. If he just went back and forth, right? And that way he could test if his serum was making the difference, because there's nothing else important about what day you come in, right? That's just a way of randomizing for him. So he was able to do it random, give the serum on certain days, and on all Monday he would give the serum out, all Tuesday he would not, all Wednesday he would, and he would keep track of it. So, and then these were the results over the years. Many more died without the serum than with the serum, so obviously the serum was really working. That's how they prove it. That's a controlled study, right? Describe the sample. What is the sample? It's the 484 patients. That's the sample. Is selection bias a problem? It is unlikely, since humans were not involved in the selection. What does he mean? What does that mean? Humans were not involved in the selection. How were humans not involved in the selection? I thought he was. Do you realize?
Is it because it was random?
Yeah, why was it random?
Because he did the days.
It was just days, yeah. You were just being selected based on the day you came in. The doctor wasn't looking and go, yeah, I like that person, I'll give them the serum. Nah, that person's not getting. The doctor wasn't picking, right? That would wreck it. It was random. It was just the day you came in that determined whether you get the serum or not. So that means there's no selection bias. There's no biases, right? All those things are to weed out biases.